Okay, this topic then is the last topic in the inorganic chemistry section, and it's the inorganic ions in aqueous solution, it's called. Okay, and we're given two examples of ions with a +2 charge, M2, and the two examples we're given there is copper, which is, and you need to know these colors. Copper, of course, is a nice blue color. You get copper sulfate. And Fe2, which is a very, very pale green, quite a nice color. And then we've got the M3 plus ions, and of course aluminium is not a transition metal ion, so it's not colored, it's colorless in solution. And Fe3 plus, which is not a very nice color, it's a rusty, dirty brown color. So we need to know about these. Now they all exist as complexes, complex ions with water. They all form the Hexaqua complexes, including aluminium, even though it's not a transition metal. And it may come as some surprise to you that if you test the pH of any of these solutions, they're all significantly acidic. And in actual fact, the M3 plus ions, they are more acidic. They're probably, an average, 0.5 molar solution of it would be pH 3 or something like that. And these will be like pH 4, not quite as acidic. Right, let's see, why are they acidic? Right, so the answer lies in the fact that they exist as complex ions. So let's take copper as an example. Copper 2 plus, and we're going to have 6 waters. I'm only going to draw 4 of them because I can't draw it in 3D. Surrounding it, and the water, one of the lone pairs on the oxygen, there's 2 lone pairs on each oxygen, is forming a dative bond to the central metal ion. The waters are ligands. Now, because this copper is positively charged, it has a tendency to draw electric charge, negative charge, out of the water molecules. And so what happens is that will reduce the electron density in these bonds, which weakens them ever so slightly. And that means they have a small tendency to lose a proton there. Okay, so if you think, you draw a curly arrow, that pair of electrons is going to go from that bond onto the oxygen, and that is going to be, now that water will become an OH minus, if you like. So the charge is obviously spread out. It's not just on the oxygen, but you think there's 2 plus on the copper and a 1 minus on the oxygen. Okay, and it's, as I say, it's caused by the electron withdrawing effect of the central metal ion. Now, if you think about a 3 plus ion, you'll be able to see that that's going to be more electron withdrawing. So the Fe3 plus ion is more acidic than copper 2 plus. Okay, so it's more electron withdrawing, and so it's more acidic. Right, so you can actually work out these are bronzed-Lowry acids, these complex ions. So let's think of the Fe3 plus. So it's going to be Fe H2O 6. That's the acid. Gives away a proton. It's going to be Fe H2O5 now. OH, just one OH, don't need brackets for it then. And the charge on that is going to be 2 plus now. And we have got a proton. So if you refer back to the, we're talking about acids and base topic, this is the weak acid, and this is its conjugate base. And if you remember, the Ka constant, which is equal to the A minus concentration, the weak acid, and the hydrogen ion concentration over HA. And for the iron 3, the hydrated iron 3 ion, that's Ka is equal to 6 times 10 to the minus 3 mole per decimeter cube, the units. And if you compare that to the Ka of ethanoic acid, carboxylic acid, that's 1.74 times 10 to the minus 5. So it's actually 100 times stronger, again, more than 100 times stronger than ethanoic acid. It's considerably acidic, right? And that goes for all four of the ions here. Of course, the Ka value for copper, because it's only 2+, is going to be not as big as that one. I couldn't find a value for that, but it would be smaller than for the iron 3+. Right, now, if you've done about Lewis acid theory, this, if you've already done the oxides of period 3, which is I think it's section 2.4. If you've done that already and you know what a Lewis acid is, just refresh your memory. Actually, what's a Bronsted-Lowry acid? Is that's an H+ donor, isn't it? A Lewis acid, slightly different theory of acids. They are Lewis acids are lone pair acceptors. Okay, so if we think about if we think about like a copper 2+ and anhydrous copper 2+ ion, right, that is a Lewis acid because, of course, if you add water to it, what happens? It accepts a lone pair, accepts several lone pairs, and to form the complex ion. So that's a Lewis acid, and then once you've got this, add water to it, you end up with this can give away protons, so this is now a Bronsted-Lowry acid. And we've seen that trend before, if you have done 2.4. So for example, SO3 is a Lewis acid. And when you add water to it, add water to SO3, what do you get? You get sulfuric acid. And that is obviously now a Bronsted-Lowry acid. So it's the same sort of thing. Right, so what this means is that all of these complex ions, also that we're interested in this topic. So, all of these, then these are the Hexaqua species we're talking about here, which is shorthand, we've just written them like that, but they're all Hexaqua. They're all acidic. And that means they do react with bases. They'll react with, and we have to know how each of them reacts with the following bases. With the OH- ion, NaOH, we have to know about that. How they react with ammonia, which is a base, of course, and also how they react with the carbonate ion. Now, that's a very weak base. It's a much weaker base than OH- or NH3. We have to know how they react with that as well. So we'll cover those in the next videos. But just this introduction is just an idea that these Hexaqua complexes are all weak acids.